Hello and welcome to Ansys-Tutor. In this tutorial, we would see how you could simulate a sloshing problem in ANSYS Fluent without using any UDF. For this simulation, we had taken two different liquids in a glass, one is denser than the other. The rest part of the glass on the top is filled with air. We would observe the mixing between these two layers due to sloshing. Without using any UDF, we would apply the sloshing effect on the fluid. Let's know the main learning points from this tutorial. You would learn the application of Revolve Tool in the creation of a 3D axisymmetric geometry. You would learn how to slice a 3D geometry body into various parts. In solver setup, we would see how could you set up the solver for a sloshing simulation without using any UDF. Finally, in results, we would generate an animation video of the simulation which can be used for analysis as well as presentation purposes. At first, let's understand what is sloshing. It is the motion of a free surface liquid in a partially filled container. It is the movement of liquid inside another object which is under a motion. Let's understand it practically. Suppose we have a glass that is half filled with water. We move the glass forward then move it backward. It would cause an undulation of the top free surface of the water. This phenomenon is called sloshing. So let's know how could you simulate such a problem in ANSYS Fluent. At first, we would start with the creation of the fluid domain geometry. Right-click on Geometry and select New Design Modeler Geometry. Select the XY plane. Click on the Z-axis to make the sketch normal to the screen. Change the default units to millimeters. Select the sketching. Select the polyline tool. Draw the sketch. Put the dimensions. Click on Generate. Select the Revolve tool. Select the sketch. Select the axis of revolution. Click on Apply. Change the operation to Add Frozen. Click on Generate. Now insert a new plane parallel to ZX plane. Make the new plane at an offset along Y-axis. Similarly, create another plane at an offset from the new plane. Put the offset distance as 70 mm from plane 4. Now we would slice the geometry into 3 parts. For this, Click on the Slice option. Select Slice type as Slice by Plane. Select Plane 4 as the base plane and click on Apply. Then click on Generate. It would slice the geometry into 2 parts at the Plane 4 location. Again, select the Slice option. This time select the second new plane, that is the Plane 6 as the base plane, and click on Apply. Click on Generate. Now, we can see the geometry is been divided into 3 parts. Select all the parts, right-click and make it into 1 part. Save the geometry and close the window. Now we would proceed to mesh this geometry in the ANSYS meshing workbench. Open the meshing. Right-click on the mesh. Select Method. Hold Ctrl key and select all the 3 parts and click on Apply in the geometry box. In the method, select Sweep. Click on the mesh. In the Details of Mesh, go to Sizing, select the Use Adaptive Sizing option, and make it Yes. In the resolution, enter the highest resolution value, that is 7. Right-click on Mesh and select Generate Mesh. The meshing is done successfully. Now we would provide name tags to various boundaries and zones. Select the Volume Selection tool. Select the top part, right-click, select Create Named Selection. Enter the name as Air Domain. Similarly, select the middle part and name it as Liquid 1. Select the third part and name it as Liquid 2. Select the Face Selection option. Select the top surface of the glass and name it as the top outer wall. Meshing and named selections are complete. Right-click on Mesh and select Update. It would link the meshing to the CFD solver. Close the meshing and proceed for solver setup in ANSYS Fluent. Keep the single precision model and click on Start. As it is a 3D multi-phase flow problem, the single precision model would take lesser time to produce the result than the double precision model. Check the quality of the mesh in the solver. Check the meshed cell size. Make sure that the minimum volume should not be negative. Select the transient solver. Go to Models, change the viscous model to laminar. This is to reduce the iteration for turbulent equations. Select the species model, select the species transport model and click on OK. After adding the species transport model, you could able to see the mixture model in the material. Now go to Materials, select the fluid and open the Fluent Material database. Enter the name of the material as Liquid 1. Enter the density as 900 kilograms per meter cube and viscosity as 0.001 kilograms per meter second. Click on Change Create. Then click on No to create it as a separate material without deleting the material properties of air. Similarly, put the material properties of the second fluid. Make sure that you have 3 materials in the Fluid Material section including the default air. Now click on the Mixture template. Change the name as the Liquid Layers. In the Mixture species, click on Edit. Move the Liquid 1 and 2 from Available Material to the selected species and remove all the default selected species. Click on OK. Change the density to volume-weighted mixing law. Change the viscosity to mass-weighted mixing law. Click on Change, Create to save the material properties for the species. Close the material window. Now go to Models and select the multi-phase model. Select the volume of fluid model. Select the formulation as implicit. In the body force, formulation checkbox, select the implicit body force option. Then click on Apply. Now switch to the Phase tab, select Phase 1, name it as Air. Select Air from the Phase Material drop-down menu. Click on Apply. Select the second phase and name it as the Liquid Layers. Click on Apply. Close it. Turn off the energy equation. Open the boundary conditions. Sort the boundaries as per their type. Select the top outer wall and click on Boundary Type drop-down. Select a pressure outlet boundary condition, as we want to keep the glass top surface open to the atmosphere. Make sure that the liquids would not go out from the glass by making the species mass fraction and multi-phase backflow volume fraction as 0. Click on OK. Select the operating conditions. Now we would insert the acceleration values into it. For this, go to Named Expressions. Create a new expression. Name it as sloshx dot. before writing the expression, let's know about how this expression is generated. At first, we have provided a maximum displacement of 50 mm in a simple harmonic motion. Which means the glass will be displaced 50 mm along x-axis direction, and then it will return to the mean position, then 50 mm along the negative x direction, and return to the mean position. And all this would be done within 1 second of the time period. This linear simple harmonic motion can be written as 0.05 sine 2 pi into time. Taking derivative, this expression is converted into velocity, and then taking the derivatives of velocity we obtain the expression of the acceleration. The expression of acceleration would be put in the operating conditions in this simulation. So write down the expression for acceleration in the definition box with all the units. Click on Refresh to check if there is any error in the expression. Then click on OK. Now go to Operating Conditions. In the X acceleration box, select the expression option. Now enter the name of the expression in the box. In the Y acceleration, keep the default gravity. Click on OK. Click on Solution Methods. Select Piezo. Keep the default values. Go to Initialization. Select Compute from all zones, then click on Initialize. This is setting all the initial volume fraction of liquids inside the domain as 0. Now click on the Patch option. Select the phase as the liquid layer species. Select the volume fraction as the variable. Put the value as 1. Select the zone as liquid 1 and liquid 2. Click on Patch. This means we have filled the 2 layers of the liquid with the secondary phase, which is the liquid layer species. The remaining top layer will be filled by the default primary phase material, which is the air. Now we would distinguish the material in each of the liquid layers. For this, select the liquid 2 and enter the volume fraction as 1. Select the zones to patch as the liquid 2 zone, then click on Apply. It will put the material of liquid 2 in the respective zone. Close the patching. Now we would set the animation for the simulation. For this, go to Calculation Activities. Click on Solution Animations. Select the storage type as in memory. Click on New Objects and click on the contour. Select the contours of phases and the liquid layers as the phase. Click on New Surface, select Plane. Select the XY plane, as we have given acceleration input in X direction, so we can observe the animation properly on this plane. Click on Create. Select the surface as Plane 6, then click on Save Display. Change the view. Enable the time advancement text box. Select the contour as the animation object. Set the view. Then click on OK. Similarly, create another contour for species mass fraction. to observe the mixing between the two liquid layers. Now go to Run Calculations. Put the number of time steps as 400. Time step size is 0.01 seconds. As we are going to observe this simulation for 4 seconds. Now click on Calculate. As this is a 3D transient multi-phase simulation, it would take a long time for the calculation to get completed. After the calculation got completed, save the file. Go to the results. Select the animations option. Click on playback. In this, select the animation file in the animation sequence and click on play to watch the full solution animation. In the write or record format option, select the MPEG option. Then click on write. The solver now would create the animation file as MPEG video format. Similarly, create the second animation video file. Now where to find these files? Go to the Workbench file folder. Open the folder DP0, open FFF1, then Fluent. In this folder, you can get those animation files. Select these files and copy them. Create a new folder in your computer and paste these files over there. This is because, if you want to further change any parameter in the setup file or initialize again, you would lose these files. This is the solution animation obtained after the calculation got completed. It can be seen from the animation that the sloshing of liquid layers is done successfully for a period of 4 seconds. In this animation, we can see the mixing between the two liquid layers due to the sloshing effect. It can be seen that there is only some partial mixing between the liquid layers within a time period of 4 seconds. In our next tutorial, we would observe the effect of swirling on the mixing of the liquid layers. Let's conclude the demonstration. If you had learned something new, then please hit the like button. If you are new to the channel, then please subscribe. Comment below for any queries or suggestions. Thank you. Stay healthy, stay safe.